Hello, welcome to Chik-Wauk. This is a great crowd, so thanks for coming to Chik-Wauk. I'm Renee Block, and I'm a volunteer here, and I'm on the board of trustees, and I have the very strange and awkward position of introducing my husband, who's the speaker. So. And the yin and the yang, the artist and the scientist. And the strangest thing about being married to a meteorologist is people come up to me and ask me weather questions. Like, why would I know? So they think that because we live together, I should know the weather. But I don't. But I assure you he does. And so, my husband, Chik-Wauk.
That is a strange introduction. And she knows more about the weather than she lets on. Thank you, everyone, for coming up here today. Obviously, I'm going to talk about the climate of the Gunflint Trail. But, of course, we're experiencing some climatologically unnormal conditions here over the last day or so. We're going to talk a little bit about that and see how things have developed and where things are going to go. If I can get this to go, there we go. I'm going to talk about the definition of climate and then look at the past climates. The climate here has not always been the same. In fact, climate is constantly evolving. And I'm going to talk about why that is and how that works. We'll look at the current climate and some future climate scenarios, and then we'll look at the impact of some of these climate changes on the trees, the wildlife, some of the things that we all really treasure here on the Gunflint Trail. The definition of climate, according to the Bible of meteorology, the glossary of meteorology, is the slowly varying aspects of the atmosphere, hydrosphere, land surface system. Notice how all-encompassing that definition is. Climate is more than just the atmosphere. It's more than just what happens in weather. It's that combined with its impacts on water, and where water goes and how water moves from the ground to the air and back again. And of course, that water and that air's impact on the land surface system. Temperature and precipitation are the key variables that we use to measure those changes, but obviously there are a lot of other weather variables, but we're going to focus on temperature and precipitation, especially as we look at past climates, because those are the ones that we can easily track and measure. Now, I want to draw a distinction between climate in that broader definition that I just gave and what you often hear as climate normals. The normals are a convention of the World Meteorological Organization, which defines a normal period as the weather averaged over the past 30 years. The normals are updated once a decade. The most recent period was from 1991 through 2020, so we're just into the new normals. But implicit in that definition is the fact that normals change. Every decade, things change. And that's been recognized for well over 100 years. So when we talk about climate change, really, climate evolves. And climate evolves according to forcing. But we still define it at the very shortest period of time as at least a period of 30 years. A colleague of mine at DTN, where I worked for 40 years, had a better definition, I think. Climate is what you expect, weather is what you get. Climate is weather if you're averaging it over a long period of time. Now, there are other factors in addition to just temperature and precipitation. What you're looking at here is a map of Minnesota and its land cover, and as you would expect, the western and southern portions of Minnesota are primarily cropland and crop cover, and up here in the northeast, it's primarily forest of whether it's deciduous or coniferous. But land cover is determined by climate and by terrain and topography. And one of the most distinctive features of the Gunflint Trail is the tremendous variety of those features. In fact, topography, which is this diagram here on the left, is a considerable factor. When you are in Grand Marais, where you're right on Lake Superior, you're at an elevation of 604 feet above sea level. By the time you get to the top of the hill, you're at 1,500 feet above sea level. And by the time you get to the Laurentian Divide, just past Trail Center, you're almost at 2,000 feet above sea level. As a matter of fact, the highest point in Minnesota, Eagle Mountain, which is just south of here by 20 or 30 miles, is 2,200, over 2,200 feet in elevation. So between Trail Center, halfway up the Gunflint Trail and town, is a rise of nearly 1,500 feet. And when the winds are out of the south or out of the east, that air is being lifted up over that terrain. And as a consequence, there's a tremendous difference in precipitation totals between Grand Marais and the top of the trail. And here, at the end of the trail, we're right up there in that little crook there, what goes up into Lake Saganaga, and we're actually slightly lower than our mid-trail. So the topography defines the watersheds here. As I think a lot of you know, the Laurentian Divide is in fact a continental divide, and all the water east and south of the divide flows into Lake Superior and out into the Atlantic Ocean. Everything north of there flows eventually up into Hudson's Bay and to the Arctic Ocean, although it does go, it's all part of the Rainy River watershed. And this entire part of Minnesota, the dark green and the light green, all this water flows north. Everything here, of course, is in the Mississippi River watershed and flows south into the into the Caribbean Ocean. So watersheds, topography, these are other things that are forcing functions that impact climate and, of course, impact land use and wildlife. Now I want to take a step back in time and take a look at past climates here on the trail. And we go, what did Rocky and Bullwinkle say? Into the Wayback Machine. In fact, it's a very well-defined climate system that's been stable. This chart goes back 400,000 years, but in fact, this record goes back at least 1 million years of very well-defined cold periods, ice ages. These are temperature, this is 0 degrees, is not 0 degrees centigrade, it's temperature change from the present. So the average global temperature in an ice age is 6 to 8 degrees colder than it is today. We're here, way at the end of this record. But this ice age cycle of 100 to 120,000 year periods of an ice age. During an ice age, there's a mile of ice on top of this location right here where we are. But then a very sudden, rapid warm-up. The temperature is very similar to what we have today, much warmer. The glaciers melt, the ice recedes, and we go into one of these interglacial periods that typically last anywhere from 10 to 15,000 years before the cycle repeats. This cycle is called the Milankovitch cycle, for the guy who figured out that it was the precession of the Earth's axis. And it gradually, at times, tilts a little more towards the sun. We get a little more solar energy, and that is enough to change the heat balance of the Earth system and the climate system and allow things to warm up. But this cycle that you're looking at, when I was in graduate school in the 1970s, this was what we expected the future of climate to be. It was an oncoming ice age, because we're getting to we're 10,000 years into the current interglacial period. But things are changing, as we all know well. If we look down, scope that time from 1 million years down to the last 10,000 years, now we're into the time frame of this interglacial period. And 10,000 years seems like a long time, but really, for us, we have we don't have a geological sense of time, we humans. So we are very much in the present. This period of 10,000 years represents all of civilization. It was in 8000 BC that grasses were first domesticated in the beginnings of agriculture that enabled people to stop hunting and gathering and instead start devoting time to raising crops and living in larger groups. And you can see that the temperature scale has changed. It's still the difference from current temperatures, way up here at 0 degrees. And it was warmer by a few tenths of a degree through much of that period, with a slow, steady cooling over the last 5,000 or 6,000 years, typical of the end of an interglacial period. And then, bang, right here in the last few hundred years, we see this tremendous spike. Now, I want to add right from the start that all of these graphs and charts I'm going to show you come from the Intergovernmental Panel on Climate Change, the IPCC, which is a United Nations organization that has been monitoring climate now for the last 30 years. Every 5 years, they issue an updated report and forecast. The latest one was just completed in 2021, and a lot of these graphs are from it. And they continually do analysis of the past climate, and then I'll also be presenting some outlooks from the IPCC on future climate based on this science. These reconstructed temperature patterns primarily come from ice core samples from glaciers in the Antarctic and Greenland, in many different locations, because that ice goes back nearly 1 million years in some cases. We can reconstruct temperature profiles from that, and we can also reconstruct the atmospheric gas consistency. What are the trace elements within the air that's trapped in that ice? So let's move forward. Let's scope down again. Now we're looking at the last 2,000 years, actually the last 2,021 years, going back to the year 1 of the current era all the way to present. And what you see is that we're in this same very steady pattern of very little change from present temperatures until you get to about 200 years ago. This is, in fact, the 1830s, the invention of the steam engine, is this dashed line here. And beginning after that point, that's when we began the large-scale mining and burning of coal first, and then other hydrocarbons, oil and natural gas. And the carbon dioxide level in the atmosphere remained very constant through most of this period, through most of these 2,000 years, very much at the average that we see in every one of the interglacial periods going back in that record from a couple of slides ago, until that. Last year it was at 416 parts per million. So the amount of carbon dioxide in the atmosphere continues to increase at a virtually an exponential rate. And that is a large part of what's driving the warming, because it is a greenhouse gas, it traps heat and results in the warming of the atmosphere. Finally, we do have, over the last 125 years or so, really good observed temperatures. We don't have to infer it from ice core samples and things. we can actually measure it, and that shows the same, very much the same pattern of warming, sudden warming. Now I'm going to zoom in even further to the last 100 years. And when we look at the last 100 years, as we zoom in time, we can also now begin to zoom in geographic focus. Prior to this, we've been looking at global average temperatures. Now we're looking here just at the state of Minnesota and looking at the average temperature here in the upper chart. That 40-degree line with the yellow is the mean temperature, averaging summer and winter temperatures for all the places in Minnesota through time. The blue line is the actual measured average temperature. And then what we see is that things were relatively constant from 1895 right up to about 1970. And then there's a distinct shift upwards, a trend upwards in that average temperature, and the amplitude also changes, the difference between the highs and cold years and warm years, this would be. And when we see that same thing, when we focus even further down, this is focused just on northeast Minnesota now. So essentially just Cook Lake and St. Louis counties. Same time period, from 1895 right up to the present. And as you might expect, we see a considerable variation year to year, but the same distinct trend starting in 1970 of things steadily getting a little bit warmer. So we see it here, we see it statewide, we see it globally. Staying in the last 100 years, now when we're looking at warmer temperatures, that's a good thing, right? Here in Minnesota. Well, warmer temperatures, warmer air can hold more moisture. In fact, the amount of moisture that the air can hold increases exponentially with temperature. It's not a linear relationship, it's exponential. So when the air is warmer, we can expect more precipitation. What you're looking at here on the left is a chart that was put together by the National Climate Assessment for Minnesota of the change in temperatures between the period from 1900 to 1960 and 1990 to 2012, and fairly distinct pattern of warming, especially in the northern part of Minnesota. Not as much warming up here in far northeastern Minnesota. We're going to see that pattern repeated. But there's a very distinct change in precipitation, in the total amount of precipitation. Back in the 1890 to 1920 normals, we got about 27 inches of precipitation. By the 1950s, we were still in that range, but things were starting to get wetter. And in the most recent period now, parts of right along Lake Superior and in town are getting well over 30 inches of rain a year, and we're seeing our precipitation totals jump up to from 26 to 27 to 29 to 30 inches, even up here at the end of the trail. That's a 10% increase. So it's fairly significant change in terms of the amount of precipitation that's enabled by that temperature change, and that, of course, is going to have a profound impact on the plants, the flora, and the fauna that we find here. So where are we today with our current climate? Whoops, now I've got to go back. Emma told me this. Oops. So today, when we're talking about precipitation, you can see there's a very distinct pattern here. Here we are up in northeastern Minnesota, and the main thing to note is that we talked about that climate forcing from the topography. With the winds out of the south or out of the east, that air is being lifted up over this higher terrain that's out here, and we see a correspondingly big change in the amount of precipitation. Right up there, you can actually see hints of red here, right along the shoreline of Lake Superior. They don't get much rain in town, not nearly as much as you get just a little ways up that hill. And, you know, this is 27 to 30 inches. By the time you get up to into the green here, you're talking at 33 to 35 inches of rain. And if you get way up into that highest elevations here, around Trail Center, you're looking at some areas that are getting upwards of 35 to 40 inches of liquid equivalent precipitation a year. So a significant difference between there and here where we are. Here it's probably 10 to 15% less precipitation than the Trail Center. But it also translates into the amount of snow that we get. So our normal annual snowfall now, if you're from the Twin Cities, you know, you're pushing maybe 50 inches of snow a year. But by the time you get up here, you're looking at anywhere from 75 to 100 inches of snow a year, but predominantly from Trail Center south to the top of the hill. Get north of that, get up toward here, our snowfall is probably 2 feet less than it is in Trail Center. And temperatures. Same sort of thing. Looking at the difference between high and low temperatures. The first and the biggest thing that jumps out is the effect of Lake Superior. We have the normal maximum temperature in July, much colder in town than it is up here at the end of the trail. There's a 10-degree difference. The same thing is true in January with the normal minimum temperatures, but it's exactly reversed. The normal minimum temperatures here are 0 degrees Fahrenheit, but by the time you get up here, the normal average temperature, average low temperature in January, here, 8 below. So when you average these two things together, you end up with a normal mean temperature for the annual, and you can see that this is the coldest part of the state of Minnesota, and rightfully so. but it is 10 degrees different, 10 degrees colder than the Twin Cities metro area, for example. So a big change. There's one other fun fact. This average annual temperature translates directly into the subsoil temperature. Those of you who live up here will laugh at that because there's no subsoil, it's just rock. But in the rest of Minnesota, that subsoil, that average mean temperature is, you go down 6 to 10 feet. That's the temperature that the earth will be because it never changes. That's the average of the summer, the warmest in the summer, the coldest in the winter. And that's also where they try to set the depths for water mains and things so that they're below the frost line where they can't be penetrated. Up here, we're right on the edge, you know, there's almost no safe depth for water mains. Okay, so let's talk about where this is going then. So we know we're in a cold place right now. We've seen that the temperature trends have been for things to get warmer. This chart, right from the IPCC, is a forecast. This is the last 100 years. This goes from 1900 through 2100. And this is the parts in gray are the actual temperatures, and then these are the results of I think it's well over 100 different climate models that the IPCC runs from scientists all over the world, looking out over the next 80 years, what's going to happen. So the spread gets bigger as we go out in time because there's more uncertainty, but this is a pretty consistent trend toward warmer temperatures.
We can't see from the back. How much warmer are you looking at? I can't see the graph from here.
This is from present, this is a increase of 2 degrees C. So about 3.5, 4 degrees Fahrenheit. Again, average temperature change. So That's more change in the next 80 years than we've seen in the past 200. So it's a significant increase, but the change is going to be happening faster in other parts of Minnesota than it will be here because of Lake Superior and our proximity to Lake Superior. That lake is going to dampen the temperature increase a bit. So hence, my forecast for the next 100 years is that temperatures will continue to warm, but it'll be more slowly than the rest of the state. Similarly, when we look at precipitation and its trend toward increasing amounts of precipitation, the climate models again are pretty clear that they expect a moderate increase in precipitation, but what we're looking at here is a much more subtle change on the order of a few inches of precipitation on an annual basis. Now let's scope it down to the next 10 years. In my job in the private sector of meteorology, I wrote several papers specifically on looking at this for our business clients. What can we expect to see? What's the impact of climate change going to be in the next 10 years? Since a lot of these changes looking at 100 years are scary, but not highly actionable in the short term. And the thing that we should be thinking about more than anything else are climate extremes. These are heavy rain events, I did put these slides together like a week ago. I didn't order this up just to emphasize my thought. But heavy rain events, like the one we just seen, those are extraordinarily unusual in the climate record, going back to the last 100 and some years. But they're occurring with more frequency. A year ago, we had a drought. A year ago, we were in a stage 3 drought here. So big swings from drought to wet, the corresponding floods, the danger from fires, especially here on the trail when we're in those dry drought years. The chart on the left here is a chart from the NOAA's National Center for Environmental Information. They've put together a climate extremes index in which this is focused just on the upper Midwest. So it's Minnesota, Iowa, Wisconsin, Michigan, Illinois, I believe. And what they're charting is the percentage of area that is impacted by drought or floods or heavy rains every year from 1910 through 2021. And the mean is at about 20%. So on average every year, about 20% of the area in the upper Midwest would see an impact from one of these extreme events. But it's very clear that since 2000, we're seeing a lot more, a very rapid increase in these extreme events. And they did this, and they did it using the area, the percentage area, because that's a relatively normal thing. If you try to do this sort of study, and you do it in terms of the economic impact, the dollars, it's hard to normalize the dollars and damage and things like that. But when you look at it just in terms of area, you get a better understanding of how these things are changing and increasing over time. Why are we seeing more extremes? Well, one of the areas that's changing the most rapidly is the Arctic. It's warming at a much faster rate than other parts of the Earth. And the Arctic Ocean, in fact, I talked with one climate scientist a few years ago who said, it was older than me, by the way, who said that in his lifetime, he expected that the Arctic Ocean would be ice-free in the summer. The temperature changes are so extreme. When that happens, so I'll get on my soapbox again about another thing that I don't like, the polar vortex. If you listen and read the paper, you'd think that the polar vortex only happens in the winter and it only impacts the east coast of the United States when it gets cold. Not so. There's always a polar vortex. It's the coldest air is always over at the poles where the air should be coldest, where there should be an ice pack. And when the polar vortex is normal, it's relatively strong, we get fast jet stream winds, and those fast winds keep weather systems moving. When they break down, when that polar vortex weakens, then we get a slower circulation around the pole, and it becomes much wavier, and these weather patterns can get stuck. The jet stream can get stuck in one location for weeks, sometimes months on end. This is what's happening over the west part of the U.S. here over the last few years. Every summer, this pattern gets reinforced, and there's not a strong enough circulation to break it down. So there's been a lot of research going on and speculating about this as one of the proximate causes for more extreme weather, just simply because if you get locked into the wet side of one of these systems, you'll get rain on top of rain on top of rain, and you get flooding and the corresponding impacts, or you get a drought that just won't end. So, what are the impacts of these changes going to be? Well, the DNR, the Minnesota DNR, produced this series of charts. This is before 1885. The primary range of moose in Minnesota wasn't even here in northeastern Minnesota. It was primarily in north central Minnesota. This is before there was significant logging taking place. By 1965, that moose range had shrunk and occupied just the northern part of Minnesota. By the 1980s, there were still moose found in the northwest and the northeast. In 2010, even in the northwest Minnesota, the moose it's a marginal area for moose now. And northeast Minnesota is essentially the only part of Minnesota that you still find significant numbers of moose. Moose population has been relatively stable for the last 10 years, but these kind of changes, the kind of changes that I'm talking about with the weather, with the climate getting warmer and wetter, is going to lead to changes in the browse that the moose feed on, into the plants that they depend on, and so over time, it's probably going to be less favorable for moose as we look forward. I thought the chart on the right was also very interesting. This comes from the Department of Agriculture. Those of you who are gardeners know about hardiness zones, right? We're on zone 3, or we were. As a matter of fact, as recently as 1990, the northern 2/3 of Minnesota were considered to be in zone 3, and only a section along the North Shore, right, protected by Lake Superior, was zone 4. By 2006, that area of zone 4 had shifted, zone 3 had shifted way to the north, and it no longer even includes any of the Gunflint Trail. We're all considered to be zone 4 now. Zone 4 supports a lot more deciduous trees. And we are now seeing that here, even as far north and far up the trail is right here, where we now find maple trees and oak trees that we never used to be able to survive winters. So this is the impact of climate change on other things. So I'll wrap up. If there's anything I want you to take from this, it's that climate isn't a static thing. It's always changing, and it's changing because of forcing functions from other factors. Historically, climate has been slow to evolve because the forcing has been slow to evolve, but with the dramatic rise in the greenhouse gases, we're seeing a dramatic acceleration in climate change because of that change in the atmospheric chemistry. I think the climate here along the Gunflint Trail is going to continue to change, but it'll be a change that takes place much more slowly than the rest of the state. But it will be enough over the next 20 to 50 years to change vegetation, tree covers, and impact on wildlife. What you certainly can take to the bank is that we're going to be seeing more extreme events. Floods, droughts, significant events that typically you might expect to occur every 100 years or even less frequently will now be occurring much more frequently. Thank you. And I'd be happy to take questions. Yeah.
So, one of your early graphs was the Lankovich cycle. And so, I'll do it to your side. We're up here, and we should be going this way, cooling, right?
Mm-hmm.
So, humans are the heroes, right? We've warmed the planet by domesticating plants and animals, spreading humans everywhere. We're keeping the planet warmer than it would be otherwise. We should be cooling off, right?
We should be.
And so maybe it's a good thing.
It might be a good thing. Or that Milankovitch cycle, is very interesting. The primary forcing of the atmospheric climate, temperature and precipitation, is the ocean. And what we don't know and what we don't understand very well is how the ocean circulations, we've all heard about I hope we've all heard about the global conveyor belt, right? There's a lot, for example, the Gulf Stream pulls an enormous amount of heat out of the central Atlantic and out of the Caribbean Ocean and pumps it north all the way up past Greenland, the UK, into the North Sea. That's what keeps Europe warm. That is primarily why the poles don't get colder and colder and we get back into one of these ice ages. But what happens if that Milankovitch cycle happens? We've increased the greenhouse effect, but those ocean currents, we don't really understand what can shift those things. They're primarily driven by salinity, but it's a big gamble. We could end up with something else. We could end up with more snow and maybe an amplified glacial response. I don't think we know. Yeah.
So I'm from Texas, and one of the things I love about being up here is I can tramp through the woods without worries about snakes or poison ivy. Are the temperature changes we're looking for going to be small enough that we still don't have to worry about poison snakes and poison ivy, or do we not know?
Let me talk about the climatic effects of ice on snow.
That could take a
I'm
long time.
going to defer to my wife, the master naturalist.
Poison ivy will increase for sure. Snakes, I don't think we'll have enough to have the venomous snakes, but we will see new snakes for sure. And northern Minnesota, southern Minnesota, we will get venomous snakes.
Okay. Not the answer I was looking for.
And anecdotally, I think back to being up here as a kid 50 years ago. I don't remember ticks being an issue 50 years ago.
They weren't.
And now we have ticks. Whether that is directly linked to climate, I have no idea. But it's a curious thing.
Go ahead.
Okay, every now and then you hear about theories about how humans could engineer climate change, sequestering carbon underground and things like this. Possibility, if it happens, who would decide exactly what to do? Would Canada want to go one way, Mexico another way?
Well, it is that, that is the true conundrum. Can you get consensus? Can can you act in a large enough way to really make something happen and do it for a long enough, sustain it for a long enough period of time that you could sequester enough carbon? You need consensus to do that. The science, I think, is pretty clear about what's happening and what's likely to happen if we don't change. The policies that we need to adopt to change, we seem to have a really hard time as humans changing. And, it might mean making some sacrifices that we're not willing to make. So it's a very interesting question.
So it's kind of a related question. It's always about carbon dioxide, which is really an ineffective greenhouse gas. Methane is the game, right? So if you look at methane, changes from that magic Milankovitch alteration about 10,000 years ago, that's when humans proliferated. And so CH4 production went way up, so it's like 5 times more now than it was 10,000 years ago. But the efficiency of methane as a greenhouse gas is like 20 some times more effective than CO2. That's what you got to worry about. And so nobody ever, in the media, you never hear about methane. It's like, well, we can sequester that, that's a fuel. There's all kinds of things to do with methane.
Good. John's a professor of geology. I'll defer to him.
Retired.
He retired. Well, it's all right.
But you can read the Texas newspapers, they talk about it all the time. One part of them talk about how they don't care about it, so. It makes you discouraged.
What was I going to say now? I've got a lot of similar conversations. I listened to an interview on the radio about a woman who wrote a book, might have been called No Man's Century, and talking about speculating based upon what they think might happen with climate change, what's going to happen with human migration. We've always moved based upon climate change. Maybe back when there were a few 100 million people on Earth, now there's 8 billion. Any speculation on where people can move from where to where? And I mean, my understanding is that the American military has plans on what to do in case that situation happens. I'm just curious what you think.
Yeah, it's another intense intellectual puzzle, right? About what could you do, where could you go? I had about 7 or 8 years ago, I had a fascinating conversation with a man by the name of Greg Page, who at that time was the outgoing CEO of Cargill. And he had a CEO's perspective on this problem, running one of the largest agricultural companies in the world. And his view of the world was there are 8 billion people, we're headed toward 9 billion. We're growing more slowly than we used to be, but still population continues to grow. Those people aspire to become middle class. That means their consumption of protein is going to go way up. How are we going to produce that amount of protein? So the investments that he was looking for Cargill to make were in producing more protein. Chicken, beef, pork. Where can we produce that? How can we feed people and meet that, not just the growing number of people, but their aspiration to a better life? And I think that's going to be as much of a challenge as where those people are located. Thank you very much.
Yeah.